Okay, picking up where we left off, let's talk about pseudo-first order reactions. So I kind of started to hint at that last time, and now we're going to develop the basis for pseudo-first order. So just kind of reviewing what we saw last time. So if we recall, if we've got a reaction that is first order in one reactant and first order in another reactant, we have a second order reaction overall. When we have a second order reaction, one telltale sign, remember, is that if I look at 1 over concentration versus time, I get a straight line. So that tells me something is second order. If, on the other hand, I look at the natural log of concentration versus time, and I get a negative line that looks like that, that tells me my reaction is first order. And so I just want to review these models one more time here. So recall, in this model, I've got an A plus B to make C. So we'll write that out. A plus B makes C. And now I'm looking at it on a natural log scale. And if I get these like really, really close to each other, let's say like nearly equal concentrations, and I start scaling the rate constant, you can see that it does not form a straight line. So A plus B going to products when A and B are very close in concentration does not follow this test to be first order. So what if instead we look at it as 1 over concentration versus time? Okay. Well, I'll turn my rate constant off and I'll make these concentrations both like really, really close to each other. And now as I scale the rate constant, look at that. So you can see that they are following this straight line. And if in fact I make them identical to each other, look, it follows that straight line perfectly. However, when I see these start to deviate from each other, right? Like if I make one much bigger than the other, or even just like, you know, only a little bit bigger, you can see that it no longer is following that test to be a straight line, right? And if I go back to this alleged first order case where I have natural log on concentration, if I make one in large excess, now look, it's actually in fact following that straight line. So here we've come to the conclusion now, hopefully, of what makes a pseudo first order reaction. So for a pseudo first order reaction, if let's say the initial B is much, much greater than A, then what that means is B, and I'm going to put T down here, B at any time is basically equal to the initial B concentration. So this could be 1 or 2 possible scenarios to give us pseudo first order reactions. So if we purposely make B much, much greater than A, then the second one ensues automatically. Another option is that if A and B are both the same concentration, but we're steadily supplying B, right? We're steadily adding more B as we go, such that the concentration of B at any time is roughly equal to the initial B concentration, then we'll also have this pseudo first order reaction. And that means the following. So when we write the rate law, right, that's K times A times B, if we've met one of these two conditions or both of these conditions, right, then our rate law really looks like the following. So K prime times A, where now K prime is equal to our second order K up here times the initial B concentration, right? So this would be our true second order, and this would be our, let's see, can I spell pseudo? I can't spell pseudo first order, okay? And so what that means now is this K prime has the units of a first order rate constant being 1 over seconds. And now this K right here is our true second order K, which would have to have units of liter over mole per second. Okay, because then, right, if I multiply it by the steady concentration of B in moles per liter, the liter and the mole cancels, and that gives me my 1/2 apparent unit of a first order rate constant. So furthermore, if I go and then solve this thing for A, I would end up with the following. A over A initial equals E to the negative K prime of T, right? Which, recall, what that means is the following. A over A initial, which equals E to the negative second order of K times B initial times T. So let's keep going with that on the next slide, and let's rewrite that, okay? So we noted that rate under pseudo first order conditions is K prime times A, where K prime is the true second order rate constant times the initial B concentration. Solving the differential equation for the concentration of A would give us E to the negative K times B initial times T. And now, if we were to make a graph of this, there's several ways that we could graph it. So we could graph it with A over A initial, and that very first data point at T equals 0 would be 1.0. Or I could rearrange this equation to be A equals A initial E to the negative K B initial times T. And if I make a graph of this now, then on my y-axis would just be concentration, and that very first data point at T equals 0 is the A initial concentration. Okay, either way, if we were to monitor the progress of this reaction, and now noting we can't just put time on the bottom, we actually have to put the initial B concentration multiplied by time, and thus we call that exposure, okay, which is concentration multiplied by time. Then this will give us the appearance of a first order plot that decays exponentially. We could fit this with an exponential decay, and that goes as E to the negative KT, or technically that would be K prime, our pseudo first order rate constant. Or similarly, if we just plotted as concentration versus time, right, we'd get the same looking graph where it would follow this exponential decay. All right, so now what about our time constants? Well, going back to what our rate law looks like, right, negative dA by dt equals K prime times A, where once again, K prime is the true second order rate constant multiplied by the initial B concentration. So we can do this in terms of half-life, or we can do it in terms of lifetime. So if we were to think about this in terms of lifetime, so remember tau, the lifetime of a first order reaction, is 1 over K. 2 lifetimes would be 2 over K, and we've got to be correct. We'll make that K prime, noting, right, that this is in the pseudo first order. So let's write that down. 1 lifetime, 2 lifetimes. And recall, 3 lifetimes will basically be 95% of A has been consumed. Well, now noting that K prime is K times B initial, then the lifetime of our reaction could be written as the following. So we could write it as 1 over K times the initial B concentration, where now that K is the true second order rate constant, and B initial is our, our initial concentration. Okay. So so very, very similar to how a first order reaction would go with all the same types of calculations. However, again, we've imposed the following condition where B at any time is much, much greater than B initial. Or excuse me, that is the wrong way to write that. Where it's A initial is much, much greater than B initial, or B at any time is roughly equal to the initial B concentration. So either scenario results in B not changing in time and thus can be treated like a constant. And so as it turns out, when you're doing experimental kinetics, if you are studying a true second order reaction, 95% of the time you do that in pseudo first order conditions to make the experiment easier to follow. Because now you only have to follow the concentration of one reactant instead of having to follow the concentration of both reactants simultaneously. So it does make that much easier to do experimentally. Okay, folks, I'll see you in the next video.